In this video I'm going to cover ideal gases. We start with 3 experimentally determined gas laws. I'm going to be using some properties of gases. I'll write those down. Pressure, pressure, volume and absolute temperature. Gas laws use absolute temperature, so it's vital that you do any conversions from Celsius into Kelvin before you do any calculations with the gas laws. That applies to all of them. All 3 gas laws that we're going to look at apply only if the mass of the gas is kept constant throughout the changes in other properties. In addition to the fixed mass of gas that they all have, each one has another property kept constant. Firstly, Boyle's law says that for a fixed mass of gas at constant temperature, the pressure is inversely proportional to the volume. And that means that P multiplied by V will be constant. So constant temperature. That means that if volume is doubled, the volume of the gas, then pressure will be halved, or if the volume was decreased to a third of the initial, then pressure will be tripled. Okay, Boyle's law. Next up we have Charles's law. Volume is proportional to the temperature, so V over T is equal to constant. So because it's directly proportional, the volume divided by the temperature is equal to a constant. In addition to the fixed mass of gas, the other property, pressure, needs to be kept constant also. Okay, so double the temperature, double the volume, and so on. Bearing in mind, in addition, that this is absolute temperature, so that's the place where you have to do conversion. Then there is the pressure law. Pressure is proportional to the absolute temperature, fixed mass of gas, and volume must be kept constant for that law to apply. Alright, so those are our 3 gas laws, and upon that we have an ideal gas law. It's based on those 3 laws there. An ideal gas is a theoretical model. An ideal gas obeys all of the gas laws perfectly. So that's what it is. And let's write this down. Ideal gas law. So we combine all 3 relationships. Okay. So P P is proportional to T over V, and that means that PV divided by T is equal to a constant. The gas constants from that relationship are experimentally determined. Now I said constants plural because there's two ways of looking at a gas. The amount of gas that is you have. So for our gas constants, you can either, for the amount of gas you're looking at, think about it in terms of how many moles of gas you have, or how many molecules you have. So for the number of moles, we'll start with. The proportionality constant here is nR. So PV over T equals nR. Often stated in that form there. So we have these terms in the equation here. N, that's the number of moles of gas that you have. R, is the molar gas constant. That value is on the data sheet. Right, what if you have a number of molecules of gas? The relationship now is PV over T equals NK. The N is different this time, it's a capital N. N meaning number of molecules, K being the molecular gas constant, which is called the Boltzmann constant. So it's the molecular gas constant with those terms there. Both equations work in the same, they'll give you the same answer for this equivalent data. So N and the two N's are related, the number of moles and number of molecules. One mole of gas has Na molecules, that's the Avogadro constant. Times 10 to the 23. That doesn't have any units because it's just the amount of molecules in one mole. So that's how N and N would be related. Both of the constants are on the data sheet, so you refer to that data sheet when you have an equation, when you have a question requiring the use of them. Okay, let's have a look at actually using the gas laws, these proportional relationships. Like most things in physics, we look at initial conditions, something happens to whatever we're observing, and we have final conditions for that system that we're observing. So you have initial, which we call 1, and final conditions 2. So anything with a subscript 1 is an initial condition, and anything with a subscript 2 is a final condition. If pressure is inversely proportional to volume, then P1, V1 is equal to a constant. And that means that P2, V2 will also be equal to the same constant, and therefore they're equal to each other. In a question requiring use of this, you'd be given 3 of those values and you'd need to find the 4th one. Sorry, not P, V. For V is proportional to T, then V1 divided by T1 is equal to V2 over T2. And that applies to the reciprocal, so T1 over V1 equals T2 over V2 as well. And the reciprocal there also applies. Last one, this is the ideal gas relationship. And the initial conditions multiplied by that will give you the final conditions multiplied in the same way. So you can use that to solve, if you have 3 of these and need the 4th, you can rearrange that equation into whatever format you need with the unknown as the subject. If you didn't know T2, for example, you could take the reciprocal of both sides and then rearrange it. It's easier to do that way. What you'll notice with the use of these is that, let's say we wanted to use this, let's use this relationship. We want to find V2, okay? V2, according to that equation, is equal to V1 multiplied by T2 over T1. Here you can see that the second volume, the final volume, is equal to the initial volume multiplied by a ratio of the temperatures. That's good, the units on both sides agree, because the units here cancel out. So you always have, the same here, P2 is equal to P1, the initial pressure multiplied by a ratio of the temperatures. You always have that the final quantity is equal to the initial same quantity multiplied by a ratio of the other quantity involved. Here it's you would have a ratio of 2 quantities. So that's a good check that you've done things correctly. And that is ideal gases.